Module 01 of this Cathodic Protection Training Course provides the essential foundation for understanding the science and engineering principles that govern corrosion control in pipelines and other buried or submerged steel structures. Cathodic protection, CP, is a critical technology used worldwide to prevent pipeline failures, industrial shutdowns, environmental disasters, and substantial financial losses. Effective corrosion control directly impacts pipeline integrity, national energy security, industrial stability, and economic performance. A well-known example is the Nord Stream pipeline incident, where structural failure contributed to severe economic consequences for European industries. This illustrates why understanding corrosion mechanisms and implementing effective CP systems are vital not only for asset owners but for communities and entire countries that depend on reliable energy infrastructure. Corrosion is governed by universal laws. Scientists study these electrochemical laws and engineers apply them through practical systems such as impressed current cathodic protection and sacrificial anode systems. These same principles allow us to control electrical energy safely, from powering homes and industries to operating batteries, vehicles, and digital technologies. My role in this course is to present all scientific and technical knowledge required to understand corrosion, electrochemistry, and the practical application of cathodic protection. Module 01 is intentionally designed to be simple and accessible, helping students to build a clear understanding of natural laws before moving forward to advanced CP design, analysis, and diagnostic techniques. This approach removes the confusion, often called gobbledygook, that many encounter in traditional training. When cathodic protection operatives first begin working in the field, they must be able to relate scientific theory to the instrument readings, data recordings, and real-world conditions observed during pipeline surveys. Module 01 includes practical exercises to help students interpret field data, understand voltage measurements, and make informed engineering judgments. Since the 1980s, cathodic protection survey data has been stored in computers. However, the gap between electrochemical theory and conventional field practices has made true computerized analysis extremely difficult. Most CP programs today rely only on displaying voltage graphs. Typically, the well-known negative 850 millivolts criterion measured with a copper-copper sulfate reference electrode, and many assume protection is achieved when this number appears. Module 01 explains clearly why this interpretation is incomplete and often misleading. This module is essential for anyone involved in CP operations, pipeline maintenance, corrosion engineering, or asset integrity management. A proper scientific understanding of the pipe to soil potential is crucial, as this measurement appears in nearly every technical paper, design document, and field inspection report relating to cathodic protection. Cathodic protection practice has long been divided between electrochemical science and practical field implementation. The scientific definition of the required measurement comes from laboratory conditions where variables are completely controlled within a closed electrochemical circuit. In field work, we refer to the working electrode as the anode and the return electrode as the cathode. However, the IR drop described in scientific literature is not the same as the IR drop in the soil commonly discussed during field surveys. True scientific measurement requires capturing the potential at the metal electrolyte interface, eliminating the IR drop entirely. This cannot be achieved in normal field conditions without special equipment such as the Alexander cell, which provides the necessary electrode arrangement to measure the true electrochemical potential. Science requires codified principles based on repeatable, observable evidence. Engineering must adhere to these natural laws to be successful. When engineering practice deviates from science, as often happens in conventional CP work, failures occur. This training course has been online for many years and continues to attract thousands of students, engineers and industrial professionals. Module 01 is the starting point, and students must fully understand this material before progressing to later modules. Each participant will submit a final paper for publication on the CPN website, where experienced corrosion engineers and scientists will review, validate and discuss each submission. Software engineers developing diagnostic or predictive tools for corrosion control must also understand these fundamental laws of nature. Without this understanding, accurate computer modelling of corrosion processes is not possible. Module 01 sets the foundation for everything that follows, both in this course and in real-world corrosion control.